Chapter 6. So I'm working through chapter summaries for OpenStax College Physics. I say that every time just to make sure that we're all on the same page. Chapter 6 is about circular motion and gravity. We've already talked about gravity. We're going to do better gravity. So I think it's important to kind of stop and just look back at where we've gone, just so we know when we're going over new stuff, how that relates. So here's the big picture of everything we've done so far. First, we have the definition of velocity. And I wrote this as a vector, okay? So velocity is the rate of change of position, where here I'm using r as position. It's very common to use r as position, the vector position. You could write this as Vx is delta x over delta t, Vy is delta y over delta t, but okay. And then we have acceleration is defined as the rate of change of velocity. Okay, again, as a vector. Then we have these kinematic equations. I just wrote two of them. But here, this one relates the position of an object. If you know the starting position, starting velocity, and the acceleration as a vector, you again could break this in terms of x, x0, vx0, ax times t squared, and then for y. But it's just simpler to write as a vector. And then I have this one. People love this equation, but I don't. I'll tell you why. One, it's hard to derive. Two, we'll derive this with work energy later. And three, you see, I didn't write it as a vector because you can't, right? You can't write it as a vector because you're squaring the velocity, so it has to be written as a scalar value, and that makes things a little awkward sometimes. So, but there it is. Next, we have Newton's second law, which says, what do forces do to objects? They change the motion. They cause an acceleration. So the net force on an object as a vector force is equal to the mass times the acceleration of that object. And yes, that's that same acceleration. Next, we have some special forces. We have the gravitational force, which we will change later. This is the gravitational force on the surface of the Earth. It's a vector. The mass of the object times g, which we call the gravitational field on the surface of the Earth, points straight down. This is the force due to a spring. So a spring, the more you stretch it, the greater the force it pulls. I did not write that as a vector. If you want to write that as a vector, it can get a little complicated. So you just have to look at your picture and then pick your direction. There's a more sophisticated version of that, but it's not in the book. Okay. T is the tension in a string, and there's no equation. There's no equation for that. It's a force of constraint. It's whatever it needs to be in order to prevent the string from stretching. And it's in the direction of the string. N is the normal force. Again, there's no equation. The normal force is a force a surface exerts that's perpendicular to the surface, again, to prevent the object from going through the surface. And then we have the static friction force, which is technically a constraint force. Okay. But if we can get the maximum value, the maximum static friction force is parallel to the surface. It wants to prevent the two things from sliding. That's the coefficient of static friction that depends on the two types of material interacting, and that's that normal force. And then we have kinetic friction. It is calculated even though it depends on the normal force, and it's equal to this different coefficient of friction, the kinetic friction. The end. Okay, now you're all caught up. Let's look at circular motion. Because everything we've done, well, not everything, I take that back. Okay, we did projectile motion, that's not straight line. So let's imagine that we have an object moving in a circle. I'm going to try to draw my best circle ever. That wasn't bad. Look at that. That's a pretty good circle, even though I think my dot's right there. Okay. So let's say I have a circle of radius r. The book uses lowercase r, and it starts, let's say, right here. Has a radius of r, and then it moves over here, and I intentionally put it offset. And this is some angle delta theta. Okay, so it starts right here, it ends right there, it's moving in a circular path, and the circular path has a radius r. Well, the question is, how far did it go? How far is it from here to there? Well, that's just the arc length of that circle. So I can write this arc length, I'll call it delta s. Delta s is r delta theta. If, and only if, delta theta is in radians. Okay, so that's the best unit for measuring angles is radians. because if I take this radius in units of meters, I multiply by radians, I get meters, because radians is kind of like a placeholder unit. It's a ratio type of thing. If I had the angle in degrees, I'd get meters times degrees, and that's not the same thing. Okay, so let's just a quick review. If I have, let's say, pi radians, or 2 pi radians, let's say, is equal to 1 revolution, which is equal to 360 degrees. So if I go all the way around the circle, that's 1 revolution, that's 360 degrees, that's 2 pi radians. So you can use this to convert from revolutions to radians, or degrees to radians, or whatever you want. Okay, or at the end, maybe you have the answer in radians and you want it in degrees. You can do that too. We're not going to focus on that. Okay. This is important though. Let's see, what did I put next? Okay, so we can define the rate. Suppose it's moving in a circle, we can define the rate that the angular value changes as omega. This is the lowercase Greek letter omega, and it's defined as, we call this angular velocity. And it's defined as the rate of change of the angle, delta theta delta t. And so this would be in normal units of radians per second. But you may see other units. You may see RPM, which is revolutions per minute. You may see radians, degrees per second. Those are the three most common, but you could be in a lot of things. We want to use it in radians per second. Okay, and don't worry, I'm going to give you an equation summary at the end. So let's say that I want to make a relationship between the velocity, the magnitude of the velocity for an object moving in a circle, and delta s and r and delta theta. Well, so I can write v, the velocity, as the rate of change of s. I'm running out of room. I planned poorly here. I'm going to write this up here. Omega is delta. I write too big. So v is delta s over delta t. Right? That's how we define velocity. This is not the vector velocity, because we're talking about in the direction of the path around the circle. So it does change direction. So it's kind of like a speed. So I can put in this for delta s, and I get r delta theta over delta t. And then delta theta over delta t is omega. So this is r omega. So that's a pretty important relationship. V equals omega times r. Okay. And then this is s is r times delta theta. So the change in position is the radius of the circle times the change in angle. The velocity is the radius times the angular velocity. So it's a way for us to make a connection between angular quantities and linear quantities. And that's going to be important. Okay, and over here, if omega is in radians per second and I multiply by meters, I get meters per second. So that's good. Now there is something that comes up a lot, and it is important to talk about, and that's rolling objects. So imagine I have a wheel of radius r, and it's rolling this way with an angular velocity omega. Well, this contact point right here is, if it's rolling without slipping, when it's in contact, it does not move. That contact point does not move. That means that this has to have a velocity in order to keep that contact point stationary, as though a negative of the contact point velocity. So the only way that can work is if this wheel is rolling with a velocity of r times omega. Okay, so the center of mass of the wheel depends on the rotational velocity and the radius of the wheel. And this is how essentially your car tells how fast it's going, right? It takes the wheel, it looks at the rotation rate, and you know the size of the wheel, you can calculate the velocity. So if you put the wrong size tires on your car, your speedometer's not going to be right. There's probably a way to fix that, but I don't really know. Okay, so that's linear velocity. Now let's look at something else very important. Here we have this, an object moving in a circle. Remember that the acceleration as defined as the change in velocity with respect to time. So I could write that as v2, I'm so sorry about that, v2 minus v1 over the change in time. So v1 and v2 are vectors. So if you change the vector velocity, you have an acceleration. And that is exactly what happens when we are moving in a circle. So imagine that, I don't want to put that delta S right there. So here's v1 and here's v2. And so the magnitude of v1 is equal to the magnitude of v2. So it did not change speed, but it changed direction. So if you change direction, even if you don't change speed, then you will accelerate. And let's get an expression for that acceleration. The first thing I want to do is to imagine that it's some short time interval. So delta theta is small, even though I drew it large. I can calculate the change in velocity, delta v, as v2 minus v1. So to subtract these vectors, I can just redraw them. I'm going to redraw that one right there. There's v1 as a vector. There's v2, same length. And delta v would be from the beginning of this one, the end of this one to the end of that one. So we've done vector subtraction before, and that's delta v. Right there. So right away, you see that during this time interval, the velocity changes and the direction of the change is this way, which is towards the center of the circle. So we're going to call this centripetal acceleration, but I'm just going to put a note here. It's towards center. And we can also find the magnitude. So how do you find the magnitude of this? And we're going to have to use a little geometry magic, but we can use it. Okay. So I know this is the angle delta theta. It turns out that this is the same angle delta theta, right? Because if you imagine moving this up here, then as that angle gets smaller and smaller, these get closer and closer, so they're the same angle. Now, if delta theta is small, this delta v, we're in velocity space, and that looks weird, but it's still the same similar triangle as is to this. So I can still use the same idea for that angle to find this arc length. Even though it's straight, it's pretty close to the same arc length. So I can write the magnitude of delta v as v delta theta. Why v, not v1, not v2? Because I'm talking about the magnitude. The magnitude of this and the magnitude of that are the same. So it doesn't really matter which one I put. So I'm going to put v is v, delta v is v delta theta. Okay. Now I want to get rid of delta theta. Okay. I want to get rid of delta theta. So I'm going to go back to this relationship, and I know that delta s is r delta theta. That's what we said before, right? That's the arc length. So this means that delta theta is delta s over r, and if I put that up here, I get delta v is going to be v times delta theta, which is delta s over delta r. I'm sorry, just r. Now I want to find the magnitude of the acceleration. That's delta v over delta t. So I can just take that and divide by delta t, and I get v over r delta s over delta t. And delta s over delta t is what? What? You know what that is. That's the velocity. So this is going to be v over r times v, or v squared, over r. And this is our other important thing. It has a magnitude of v squared over r. And we call this centripetal acceleration. I'm going to talk about centripetal in just a second, that word. I want to do one more thing. So we could also describe this acceleration in terms of the angular velocity. So remember that v is omega times r. So v is omega times r. So v squared, if I put that in for v squared, I get a is going to be omega squared r squared over r, which is omega squared r. So this is equal to omega squared r. They're the same thing. And just check the units on that. So this is going to be radians squared per second squared times meters. Does give me meters per second squared. So what does this say? You don't have to know that derivation. I think it's important to see it, but let's just understand what it means. AC is v squared over r. So this says that if you're moving in a circle, you are accelerating. The direction of the acceleration is towards the center. That's important. The magnitude of the acceleration increases the faster you go, and it also increases at a smaller size circle. So imagine driving in your car. There's a great question. That's a steering wheel. That's the gas pedal. And that's the brake. And the question is, what controls the acceleration on your car? And the answer is all three of these, right? Because if I push the gas pedal, I can increase in speed. If I push the brake pedal, I can decrease in speed. Those are both types of acceleration. But if I turn the steering wheel, I also accelerate because I change direction. When you accelerate in the car, you can feel it. When I push that gas pedal and I accelerate forward, it feels like I'm getting pushed back. We'll talk about that in a second. When I slam on the brake, it feels like I'm getting pushed forward. And when I turn, it feels like I'm getting pushed against the side. So you are accelerating when you turn the car. And if I turn in a smaller size circle, if R gets smaller, you can feel greater acceleration. If I'm going faster, you can feel greater acceleration. Okay. Let's talk about the word centripetal acceleration. I'm going to write two words. This is called centripetal acceleration. Centripetal. And then there's also centrifugal. Did I run out of room? I made it. Okay. So this literally means center pointing, which is what we said. This is the acceleration pointing towards the center of the circle. Now there is a thing that people talk about, centripetal force. We'll talk about in a little bit. But it's really just whatever force makes something move in a circle. It's not a big deal. This, center, fugal, fleeing. This is the force that pushes away from the center of the circle. Okay, so this is called a fake force. And we mentioned this before, but let me just remind you. Newton's second law, which says this. This only works in an inertial reference frame. That means the A of the frame is 0, technically. That's a vector. So if I'm just standing here on the ground and nothing's accelerating, my room's not accelerating, why would my room be accelerating? Even though technically it is, but we'll talk about that later. Then Newton's second laws work. I can calculate the forces, use that to find the acceleration. However, if I'm in an elevator and the elevator's accelerating up, then this doesn't work, right? If I use that as my reference frame to measure velocities. I have an extra force that pushes me down. I don't know what that is. And then we would add that in to make Newton's second law work. We would add in a fake force. That's what this is. If you're in a rotating reference frame, then in order to make this work, you have to add in a fake force that pushes away from the center of the circle. So if you're in your car and you turn to the left, you feel like you're getting pushed to the right. You're not, but you feel that way because your reference frame of the car is accelerating and you add that fake force in there. So sometimes they can be very useful, but for the most part, they're dangerous because people try to use them when they shouldn't be using them. That's a warning. Okay, so centripetal force, center pointing, we can define the acceleration like that. Let's talk briefly about forces. There's a whole bunch of awesome examples that we can do here. So I'm just going to give a very generic version of this. So imagine that I'm swinging a ball in a horizontal circle, and then so like this. And here's my ball. And I'm actually going to draw it horizontal at some point just because it's going to be easier. So now I want to draw forces on that. I only have one. It would be this tension force right there. And what we can do is use Newton's second law, F net equals ma. And I wrote that as a scalar because I'm going to use that in the direction of the center of the circle. So I'm going to choose this as my x-axis if you want to. In this case, the force would be negative the tension, and that's negative mv squared over r. So we can use this to solve for problems, but we have to freeze it in place, right? Because if I wanted to look at this a little bit later, the ball's up here, and now the acceleration is that way. So the acceleration changes directions. It makes it very, very difficult to deal with this. So you want to freeze your situation in such that you can pick the x-axis and just say, okay, it's not really always the x-axis, but at that instant it is. And this we would call the centrifugal force, because it's whatever force makes it move in a circle. Okay, it doesn't have to be that way. We could do something more complicated. We could have a ball swinging like this. So it's moving in a circle. Now I have gravitational force pulling down, and I have tension pulling up. And in this case, I would pick this as, say, my y-axis. It's not actually the y, or I can pick this as the y-axis. So now the tension is in the y-axis, and then a component of the gravity is in the opposite. But the sum of those two together would be mv squared over r. And that's a bad problem. It's confusing, but that's how we would deal with these centrifugal force problems. Okay. Let's talk about, just because it's in the book, what if you are on a rotating reference frame? Suppose I'm on a rotating platform and I have a ball. And so that ball has in this rotating reference frame, that ball has a centrifugal force pushing away from the center of motion. Now, if it's moving this way and it gets to a smaller radius, it's actually going too fast for that velocity, that position. And so one way to fix this is to give it another force, the Coriolis force. And this Coriolis force, let's see if I can get that right. Let's see, so this is V. It's going at the same velocity because, no, it curved this way. If you're on the rotating platform, it curved that way, and we call that force the Coriolis force. Okay, it gets very complicated. It's not really appropriate for this class, but I do want to show you one thing. This is also a rotating reference frame. And here's the United States, rotating. So you get a Coriolis force when you change your distance to the axis of rotation. So right here, if this is rotating and I move north, I'm closer to the axis of rotation than I was. If I'm at the equator and I move north, I'm closer to the axis of rotation, so there would be a Coriolis force. In the northern hemisphere, that Coriolis force is very, very, very tiny because it takes the Earth a whole day to rotate. But it's there, and it acts over objects that move very large distances. And one of the things that moves large distances is things like weather and water. So when water moves north in the northern hemisphere, it tends to curve to the right, okay, because it's getting closer to the axis of rotation. Now, if you've been down here in Florida, the weather's nice and warm. North Carolina is not so bad, right? Because what's happening is, because of the rotation of the Earth, we get this clockwise rotation of water. So you're getting warm water from the Caribbean up in North Carolina. It's nice. This is San Diego. The water is very cold because, again, the water is doing a clockwise rotation. So it's coming down from the north. So you get very cold water. So it's very cold in San Diego. Warm there. Coriolis force. Okay. It is important to note that this is not an inertial reference frame. If I'm standing right here in Louisiana, it's not an inertial reference frame because the Earth is spinning. And so there is this centrifugal force, if you want. We'll do that probably as a problem. Calculate the effective gravitational force due to the rotation of the Earth. If you're at the North Pole, then you're standing in water, so I wouldn't do that. If you're in Antarctica, you're at the North Pole, and you're just spinning around in a circle. You don't have a fake force. Okay, moving right along here. That was the Coriolis force. Gravity. You know, I want to talk about Newton and Aristotle because I want to. So remember that Aristotle's ideas about physics were wrong, but very commonsensical. He said that, if you drop an object, they move at a constant speed, heavier objects fall faster, which is wrong. Okay. And Galileo showed that was wrong by letting things roll down an incline and actually measuring the change in speed. And then what Newton did was they had ideas about rotational motion at the time. Okay. You could take water in a bucket and spin it, and you can see the curved surface of the water. So they knew there was some forces associated with rotation. And they also knew the moon was rotating around the Earth, orbiting around the Earth. And what Newton did was to make a relationship between objects that accelerate towards the surface of the Earth and objects that accelerate because they're moving in a circle around the Earth, the moon. And with that, he came up with the following model for gravity. He says that the gravitational force between the Earth, or really the gravitational force on the moon, that's fairly accurate to scale. It's very tiny. We'll call this M1, and we'll call this M2. He said it's an attractive force, so it points towards the other object, and its magnitude is G M1 M2 over R squared, where R is the distance between those two. So it's the product of their masses divided by the distance between them squared, and then there was a constant. And Newton didn't know what that constant was because he didn't know the mass of the Earth, he didn't know the mass of the moon. He did know the distance between them fairly well. I mean, good enough. But he didn't know the constant because he didn't know those masses. It turns out that someone did come along and measure that constant, and there's a really clever way to do it. So imagine that I take this stick, it's actually a meter stick, and I support it from the middle, just like that. And a tiny, tiny, tiny force can make this thing rotate, right? I can just tap this, rotate, because it's able to rotate freely about the center. So there was a person named Cavendish, and what Cavendish did was to take a stick like this and put masses on the end of it, and then let those masses attract other nearby masses and measure how much it rotated. And if you know something about the torsion constant of the string that holds it, you can calculate the force. You know the masses and the force, you can calculate that constant G. And the constant G, the gravitational constant, has a value of 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So that's really, really tiny. Gravity is super, super, super weak. But there's something else very important, right? Once you get that, you actually can get the mass of the Earth, and that's kind of a big deal. Before that, they didn't even know the mass of the Earth. So if you take the mass of the Earth and you stand right here, and you calculate the gravitational force on you, and we'll call this the radius of the Earth, and we'll call this the mass of the Earth, and that's your mass M, then I can calculate the gravitational force as G, mass of the Earth, your mass, over the radius of the Earth squared. And if you put in the value for the mass of the Earth, you put in the value for the radius of the Earth, you put in the value for G, big G, you get M times 9.8. That is our G, right? So the gravitational field is all that stuff, because even if you move very high, you're not changing your distance from, this is the distance to the center of the object. You're not changing the distance that much. This is pretty much constant. That's where that G is. So we have, it's important, right? We have this F weight is mg, and then we have Fg is G m1 m2 over r squared. Two models for gravity, but they agree at some level, right? Some level they overlap, and that's how our models work in science. We have models that are wrong, but they slowly diverge. So I can use this on the surface of the Earth. I can use this to fly an airplane and do a whole bunch of really complicated stuff. But if I get too far away, if I get to outer space, then I need to use the better model for gravity. And this model's wrong too. This model doesn't include things like gravitational waves, which we can detect here in Louisiana at LIGO. It doesn't include things like that. Okay, so it's still a wrong model, but it's still very useful. So models can be wrong and useful at the same time. Well, we got a lot of stuff to do here, don't we? I guess we should talk about 0g. 0g. So weightlessness, and I'd like to go first and talk about. I'm going to show you how to calculate low Earth orbit or any type of orbit, and then we'll talk about 0g. So here's the Earth, and here's an object orbiting the Earth in a circle of radius. Let's call it r, and we'll call that. We don't even care about the radius of the Earth because it doesn't matter. That's the mass of the Earth. That's the mass, and let's say that has some velocity v. Well, here we have one force acting on that object, and that's the gravitational force. I'll call it Fg. So again, I can set up this as my x-axis. I can say F net in the x direction is negative the gravitational force, which is g, mass of the Earth, mass of the object over r squared, and that's going to be mass of the object times v squared over r. So I can calculate the velocity needed to get into orbit from this equation. Notice that to be in orbit, not to get. So that r cancels with that, and that mass cancels with that. V equals the square root of g me over r. So as I get further and further and further away from the Earth, I don't have to go as fast. Now, it might sometimes be easier to talk about the period of rotation. So I could write this as g, mass of the Earth, mass over r squared is m. And I'm going to use the other expression for the centripetal acceleration, omega squared times r. In this case, this r does not cancel, but if I divide by that, I get r cubed. That mass still cancels. So I get omega squared is g, mass of the Earth over r cubed. And then if I take the square root, I get omega is the square root of g me over r cubed. So here you can see that the angular velocity, as r gets larger, the angular velocity gets smaller. But this is how we can deal with orbits, and we'll do orbit problems. But if I have a spaceship in orbit around the Earth, then it is accelerating. And so if I do a blow-up picture of my spaceship like this, the spaceship has mass, the spaceship's accelerating, the person has mass, the person's accelerating. If these two have the same acceleration, there's no contact forces needed between them. And we don't actually feel the gravitational force because it pulls on all parts of our body equally. What we feel is the normal force. So we say apparent weight is the normal force. In this case, there's no normal force between the people, and you feel weightless. You don't even have to be in orbit to do that, right? I'm going to not do it now because I'm going too long anyway. A lot of people say, oh, there's no gravity in space, so that's why you feel weightless. The gravitational force at low Earth orbit, 400 kilometers above the surface of the Earth, is like 80% of on the surface, so it's very high. But since you're accelerating the same as gravity, that's why you feel weightless. If you're in an elevator and the elevator is accelerating down at 9.8 meters per second squared, you would feel weightless. If you're in an airplane and you accelerate down at negative 9.8 meters per second squared, you would feel weightless. Okay, so there's a lot of ways to do that. Whew. Okay, Kepler's laws. I don't think this is appropriate, but it's in the textbook. So I do want to, they're cool. Okay, I'm not saying they're not cool. I'm just saying it's hard to make these connections. So the importance of Kepler's laws is that they are empirically derived based on data, right? So what you can do is you can look at the motion of a planet around the sun, and you can come up with different models. And the only important thing about them is that Newton's second law, Newton's ideas of gravity can be used to explain these, right? Before, Kepler just said, this is what it is. And then the first law says objects orbit the sun in elliptical orbits, where the sun is at one foci and there's just nothing else over there. So that's the first law. The second law says that as things move closer to the sun, they go faster. Okay, so it's going to go faster here, and we'll show that later. And over here, they're going to go slower. So what he has is this equal areas, equal times thing. So in the same amount of time over here, this area of the orbit is equal to this area of the orbit. So it's longer, so it's going to be skinnier, it's not moving as fast. I know, it's hard to see that. But then the third law, which we can derive for circular orbits, says that the period of rotation, t1 squared over t2 squared, is equal to, is that right? r1 cubed over r2 cubed. So if I have two planets orbiting the sun, and it works for non-circular orbits, but we can only derive it for circular orbits, then the time it takes to rotate squared, the ratio of those is equal to the ratio of their orbital sizes cubed. That's the third law. But the important thing, again, is that Newton was able to show that these laws agree with his model for gravity, which was kind of a big deal. This is a long chapter summary, but I'm having kind of a lot of fun. And if you're still here, I hope you're still having fun. Okay, let's just go over the main ideas, chapter summary of the summary. This is the summary. Okay, the first is this: delta S equals R delta theta, V equals R omega. So this is the arc length, radius of the circle, angular change. This is the speed, angular velocity omega, radius of the circle. We also have the definition of the angular velocity, change in theta with respect to time, in radians per second. And we're going to do more angular stuff later. Then we have the definition of the centripetal acceleration, v squared over r, omega squared times r. And we're not writing that as a vector. It's pointing towards the center of the circle. And then finally, we have the gravitational force, G, m1, m2 over r squared. This says there's a gravitational force between any objects that have mass. Okay, so me and this piece of chalk have a force between us. But since G is so silly tiny, that force is unmeasurably small. Whew, the end. But think of all the awesome physics problems we can do now with circular motion, gravity, orbits. And we're going to do more cool orbital stuff when we get into energy. But that's it for now. Chapter 6 summary. The end. Double thumbs up. See? And sparkles. Okay.